Welcome to my channel. Today I want to teach you how to find remainder in modular arithmetic. So that is the topic today. Finding remainder in modular arithmetic. In modular arithmetic. So in our examples, we look at various methods of finding remainder. Among them, we shall be using the Fermat's little theorem, which we know how it states. Then we shall also use the Euler theorem in our other examples. And then, we shall look at if we get a question that requires a method that is different from these two, then we will bring that method and do that question. But basically, the two methods that I want to use are these two. Now we know the statement of these two theorems. Like the Fermat's little theorem says that if you have two integers, a and p, where p is a prime integer which does not divide a, p is a prime integer which does not divide a, and then a raised to p minus 1 would be equal to 1 mod p. This is the statement of the Fermat's little theorem. And the condition here is that this p must be a prime integer which does not divide a. So whenever we are doing this, that we must take that into account. What about Euler theorem? Euler theorem says that if you are given two integers, positive integers, a and p, which are relatively prime, that is, the GCD is 1, then a raised to pi of p is congruent to 1 mod p. So again, here there's a condition that this p and this a must be relatively prime. In other words, the GCD must be 1. The GCD must be 1. So that is the time you can use this Euler theorem. And I've already stated the condition for using the Fermat's theorem. So if they go against this, if the question goes against these conditions, then these methods cannot be used. So let's look at examples. So we shall begin with some simple examples that do not even require these theorems. But along the way, we shall come across examples that will require these methods. So the first example that I want us to look at is example says calculate the remainder of 99 on a division by 11. On division by 11. So the question is, if you are on division by 19, let me do on division by 19. Because by 11 there will be no remainder. So on division by 19. So what the question is saying is, if 19 was to divide into 99, what would be the remainder? So in fact, mathematically, this means what is 99 mod 19? That's what mathematically, this is what it means. That this is the remainder. What is the remainder when 99 is divided by 19? And this is very easy. This one you can do it. Just divide 19 into 99 with your calculator and then find the remainder. And you'll find that the remainder will be 4 mod 19. So the remainder here is is 4. So I just divided 19 into 99. And then you find that it goes there a number of times. And there's a remainder. So the question is, what is that remainder? That's what we write here. Let's look at example 2. Example 2, calculate the remainder of, calculate the remainder of a 119 times 54 on division by 17. On division by 17. So this is also very simple. Mathematically, this is what it means. 19 times 54 mod 17. What is this? Question is, find this. In other words, what's the remainder when this product is divided by 17? Now, if it's a small product like this, you can still just multiply it. You can multiply 19 times 54, get the result. Then that result divided by 17 and see what the remainder would be. But in complicated questions, you may want to simplify this. You may want to simplify. So for me to simplify this, I'll ask myself, first of all, if 19 was to be divided by 17, what would be the remainder? I find the remainder would be 2. What about if 54 was to be divided by 17? What would be the remainder? So just divide 17 into 54, and you find that the remainder will be 3. So the question is, what about if therefore the product is divided by 17? What will be the remainder? If this product therefore, 19 alone will give us a remainder of 2. 54 alone will give us a remainder of 3. Their product will give us the remainder of 2 times 3, which is 6. So this is a remainder. But as I said, if you may want to multiply this and then divide by 17 and see the remainder. But I've said that in complicated questions, you may want to simplify the question. Find the remainder for each part and then get the product of the remainder. And that's what I've done. Okay, so the remainder is 6. Let's look at another example. Example 3 says, calculate the remainder of 23 raised to 61 on division by 17. Now here, when there is a power like this, I find it easier to either use Fermat's little theorem or use Euler theorem, depending on which one satisfies the conditions that we were given in our beginning. Now, so in fact, what this question is saying, that find 23 raised to 61 mod 17. So for me to use Fermat's little theorem, I'll check if this is prime. And if it's prime, then I also check if it does not divide 23. If it does not divide 23, then I'll go ahead and use it. So for this question, I've seen that this 17 is prime, and again, it does not divide 23, and therefore Fermat's little theorem can be used. So first of all, I'll reduce this 23 mod 17. So what is 23 on division by 17? What is the remainder? So I can see that if 23 was divided by 17, the remainder will be 6. So that means that if I were to take 23, if I were to take 23 raised to 61 and divide by 17, the remainder will be the same as if I took 6 raised to 61 and divided by 17. So the remainder will be the same. The remainder here and the remainder here will be the same. Since the remainder is the same, let me work with the smaller one. Let me work with this smaller one. The 6 is smaller here, so that I simplify my work. So by Fermat's little theorem, if this is prime and does not divide that, then we know that 6 raised to 16, 6 raised to 16 will be congruent to 1 mod 17. That's true. It will be congruent to that. But what we want is 6 raised to 61. So we want now to write 61 in terms of 16. So we divide 16 into 61 and see what we get. 61 will be 16 into 61. If you go there 3 times, 3 times this will be 48. So if you go there 3 times, is it 3 times? Sorry. Yes, let me use my calculator. Okay, so it's 3 times. Together 3 times, and the remainder will be 13. The remainder will be 13. So what this means is that I can write this in terms of this. So that means that 6 raised to 61, therefore, can be written as 6 raised to 3 times 16 plus 13, which is same as 6 raised to 16, then raised to 3 times 6 raised to 13. But this one, 6 raised to 16, we've already said is 1. 6 raised to 16 is already 1. So this is the same as 1 raised to 3, then times 6 raised to 13. And remember, we are doing it mod 17. We are doing it mod 17. So let me now create some space for us to, because this is just, you can follow. Let me just write here. You can follow from here. I'm coming to this. So this is just 6 raised to 13, mod 17. And this one I can create a square of tables. And you recall how I did this in my previous videos. So 6 raised to 1 will just be 6. 6 raised to 2 would be 36. 36 divided by 17, the remainder will be 2. Then 6 raised to 4, which is square of this, would be 2 square, which is 4. I want 6 raised to 13. So 6 raised to 8 would be 16. Because this would be 4 square, would be 16. 16 mod 17. I can write 16 or can write -1 because -1 is smaller. So I want smaller numbers so that I can easily manipulate it. So I have 6 raised to 8 being that. What I want is 6 raised to 13. You notice that if I were to square this, I would have 6 raised to 16, which would be beyond. So now I think of how do I use how do I use the ones I have to get 13? Of course, I know that 6 raised to 13 is the same as 6 raised to 8 plus, if I added 4 there, I'll get 12, that is okay. And then I will have to add 1. This is 13. So that means I have 6 raised to 8, then 6 raised to 4, then 6 raised to 1. What is 6 raised to 8? Is negative 1. 6 raised to 4 is 4. And 6 raised to 1 is 6. So this product is negative 24. Remember, it's negative 24 mod 17. Mod 17. So I ask myself, if 17 were to go into negative 24, what would be the remainder? And the remainder would be 10. The remainder would be 10. So 10 is the remainder if I took 23 raised to 61 and then divided the result by 17. The remainder would be 10. And I've used Fermat's little theorem. Let me use Euler theorem and see what I get. First of all, I want to see if Euler theorem can be used. And if it can be used, then I use it. I don't want to erase the other part because it might be similar with what I will want. So I want to check whether 23, 61, contribution by 17, whether this question can be done by Euler theorem. So I just check this number and check this and see whether the GCD is 1. Of course, the GCD is 1, so that means it can be used. So by Euler theorem, therefore, Euler theorem says that A raised to 5 of P would be the same as 1 mod P, where P here is 17. 17 is prime, so what we have there would be, let me first of all reduce this. Because I know that 23 raised to 61, we had done this and it said the remainder of 23 would be 6. It said it would be 6 raised to 61. We had already reached here. So, and then I said this is smaller, so I'd be using this. So, and I want to use Euler theorem here. 17, 5 of 17 is 16. So, this is the same as, just a minute. Euler theorem says that 5/16 is congruent to 1 mod 17. But what I have is 5 of 61. So I continue from here. From this, I come here. 16, I write 16 in terms of 16. I write 61 in terms of 16. 61 in terms of 16. So divide 16 into 61. Then it will go there 3 times, the remainder will be 13. And so therefore, 6 raised to 61 can be written as this. And so you proceed the way we proceeded from here. You proceed the way you proceeded from here and we go until you arrive at 10 as the remainder. So the only difference between the Euler theorem and the Fermat's theorem is just this bit. No, not even this bit. It's just here. Here. Just here. Because the Fermat says that it will be A P minus 1 is congruent to 1 mod P. It's congruent to 1 mod P. And you remember that for the Fermat's, this P must be prime and should be a number that cannot divide A. So the only difference, therefore, is in the statement. But the way we work out will just be the same. Let's look at another example. Another example here. Example is find the remainder of 2 raised to 1003 on division by 11. So what this means mathematically is that find 2 raised to 1003 mod 11. So I want to see whether I can use formats. This is a prime number, and this prime number cannot divide it to, and therefore formats can be used. Formats can be used. Formats little theorem can be used. Now, this number is already small, so we don't need to reduce it further. It's already small. You remember in the previous example, it was bigger than the number here, so we reduced it. Otherwise, you would even have worked with the 23 and gotten the same result. Now, since it's already small, Fermat's little theorem says that 2 raised to 10 would be congruent to 1 mod 11. And so, but what we want is, the power that we want is 1003. So we write it in terms of 10. But 1003 is the same as 100 times 3. No, same as 100 times 10 plus 3. 3 is the remainder. 3 is the remainder when 10 is divided into 1003. And therefore, what this means is that if I have 2 raised to 1003, somebody can write it as 2 raised to 100 times 10, then plus the remainder, which is the same as 2 raised to 10, then raised to 100, and then times 2 raised to 3 mod 11. But this first part here is 2 raised to 10 is 1. So we have 1 raised to 100, which will be 1. So what we are left with is therefore 2 raised to 3 mod 11, which is 8. So the remainder is 8. The remainder therefore is 8. So that is, if we were to take 2 and raise it to 1003, get the result. If that result, if we were to divide by 11, you would find a remainder of 8. Now, what about Euler? Let's see how Euler would work out. If I was to use Euler theorem, so that means Euler theorem would say that 2 raised to 5 of 11, but 5 of 11 is just 10. 5 of 11 is 10 mod 11. So you can see that R is equals to 1. It's congruent to 1 mod 11. 2 raised to 10 is congruent to 1 mod 11. So this is what Euler says. So that means again, with that, it would just be it's this. So we would proceed from here the same way and find the remainder as 8. We would proceed in the same way. Now let's look at another example. Example is find the remainder of, I want to make it different a bit, 7 raised to 1003 on division by 12. on division by 12. So mathematically, what this means is that find 7 raised to 1003 mod 12. Now, this question, you cannot use formats because this number is not prime. This number is not prime, so you cannot use formats, but we can use Euler theorem. So let's use Euler theorem. What Euler theorem says is that 7 raised to 5 of 12 is congruent to 1 mod 12. But we already know how to find 5 of 12. That one you know. If you don't know, I taught in the other video, you can check that and solve. But 5 of 12 is just 4. So these are numbers smaller than 12, which are relatively prime to 12, therefore. So that means that 7 raised to 4, 7 raised to 4 is congruent to 1 mod 12. But what we want is 7 raised to this, 1003. So this 1003 must write in terms of 4. So, but 1003 in terms of 4 would go there 250 times. And the remainder will be 3. The remainder will be 3. So that is how 4 goes there. That means that 7 raised to 1003 mod 12 is the same as, so instead of 1003 we write this. So it's the same as 7 raised to 4 times 250 plus 3. It's the same as 7 times raised to 4. Of course, this is 1 raised to 250, then times 7 raised to 3 mod 12. So, of course, this is just 7 raised to 3 mod 12. So, take 7 raised to 3, divide the result by 12, and get the remainder as 7. Get the remainder 7. So, the remainder for this is 7. So, this one you can just do 7 raised to 3 and then divide it by 12 and find what the remainder is. Look at another question. So the other question is find the remainder of 2 raised to 9 on division by 12. On division by 12. So what this means is that find 2 raised to 9 mod 12. And I notice that 12 is not prime. So that means Fermat's little theorem cannot be used. I also notice that the GCD of 2 and 12 is not 1. And therefore, the Euler theorem cannot be used. But we must do this question. There are other ways of doing it, but the way I'll do it, I'll just do it by creating a square table. Create a square table. I'll just say 2 raised to 1. What is 2 raised to 1? To be 2. What about 2 raised to 2? It will be 2 times 2, which is 4. Remember, it's mod 12. What about 2 raised to 4? When I square this, it will be 16, which is the remainder, therefore, is 4. What about when I square this? 2 raised to 8. It will be 4 times 4, which is 4. I want 2 raised to 9, so I'm there. So that means 2 raised to 9 is just 2 raised to 8 plus 1, which is 2 raised to 8 times 2 raised to 1. But the 2 raised to 8 is 4, and the 2 raised to 1 is 2. So this is 6. So the remainder is 6. The remainder is 6. No, this is 8. This is 8. This is 8. When we multiply this, we get 8. So the remainder is 8, not 6. If you want to write it, 8 more than 12. So that's the remainder. And look at what I did. Because I discovered that I could not use Fermat's little theorem, I could also not use Euler theorem. Okay. Let me do the last example. And I hope the examples we've done, you can generalize them to do all the questions involving remainders. So the other question is, find the remainder of 5 raised to 15 on division by 20. So what that is saying is that find 5 raised to 15 mod 20. And 20 is not prime, so Fermat's little theorem cannot be used. And again, the GCD of 5 and 20 is not 1. That means Euler theorem cannot be used. So that means we use the method I've used above. We create the squares. Create the squares. 5 raised to 1 is just 5. 5 raised to 2 is 25 mod 20. The remainder is 5. 5 raised to 4 is 5. 5 raised to 8 is 5. I want 5 raised to 15. So if I square this one, I'll be having 5 raised to 16, which is beyond. So 5 raised to 15, therefore, is 5 raised to 8. If I add 4 there, I'll be having 12. If I add 2 there, I'll be having 14. If I add 1 there, I'll be having 15, which is 5 raised to 8 times 5 raised to 4 times 5 raised to 2 times 5 raised to 1. And we know what this is. This is 5. That is 5. That is 5. That is 5. This is 5. This product here is 5. This product here is 5. So 5 times 5, which is 5. So the remainder is 5. The remainder is 5. And that is how we find the remainder in modular arithmetic. So we'll look at other examples next time. But if you've not subscribed, remember to subscribe so that whenever I upload videos, you can easily see them.